So I'm going to talk about isoperimetric inequalities and some applications to integrality gaps. This is based on joint work with Hamed Hatami in McGill and Avdar Megan. Okay, so the talk is going to be kind of two parts, fairly independent. The first part is about this isoperimetric inequality for Hamming cube, and the second part is applications to integrality gaps. Okay, so the story of the first talk, the first part starts with this problem of Erdos from the 70s. So this was a $250 price problem, and so here is the problem. So you have a real number delta between 0 and 1. You can assume that it's, say, 2/3 or 1/2. It doesn't really matter. And you have an integer n, which you think is going to infinity, and a distance d, which is just delta times n roughly. Okay, but it has to be an even integer. Okay. Now, Erdos asked the following question. He asked, if I have a set a subset of all the strings of length n, and it has just one property, and that property is that no two elements of this subset have distance exactly d. Okay, so you have a subset of all the strings. There are 2 to the n possible strings, and you know that in this subset, no two strings are different in exactly d coordinate. They can be different in more or less, but not exactly d. So Erdos asked, how big can this set be? And in fact, he conjectured that such a set has to be exponentially small. And it took about a decade. So here is an example. So n, for example, is 3. All the strings of length 3 are arranged in that nice cube there. And then let's say d is 2, delta is 2/3. So you connect, for example, 0, 0, 1 to all the strings which are different in 2 coordinates, 1, 0, 1, 1, 1, 0, and so on and so forth. And every other vertex is going to have 3 neighbors, so it's going to be a pretty dense graph. And then you ask, how many vertices can I select from this cube such that the endpoints of no edge is selected at the same time? So for example, here you can select 2 points. Now, so Frankl and Rodl solved this problem, and in fact, even a stronger form. And they showed that the conjecture is correct, and the set U has to be exponentially small. So the size of U divided by the 2 to the n, the set of all the strings, has to be less than or equal to some xc to the n, where xc is bounded away from 1. Okay. Yeah, so the problem we study is kind of a density version of this. Okay, so Frankl and Rodl showed that any set which does not have a pair at a distance d has to be exponentially small. So the contrapositive would be that if you have a set which is pretty big, then it should have a pair at distance exactly d. So the problem we study is exactly how many such pairs should such a set have. And the main focus will be sets of constant density, but the theorem applies to some sets which are just a little bit smaller. So unfortunately, we can't really say anything about sets which are exponentially small. So here is, for example, a way to show that there are many pairs for some notion of many. You could say that this set U is a constant density set, so I can break it into, U1, U2, U3, all of which are just slightly bigger than the bond that Frankl and Rodl have. And that would mean that inside each of these U1, U2, U3, you will have at least one edge. So you will have many edges. But this will give a pretty weak bound in the sense that the best you could hope for is, you have exponentially in n many edges, but you can never compare it to, for example, the total number of pairs at distance d. So our goal is to compare it to the total number of pairs at distance d. So a correct way to formalize this would be, for example, if I take an x at random and I take a y which is at distance exactly d, what are the chances that x and y are inside my set at the same time? And you can think about Frankl-Rodl saying that if this set is big, then the probability is like this 0. So what we prove is that this probability is at least a constant for a set of constant density. Okay. So it's bounded from below by epsilon, where epsilon is depends in some way on the density of your set and the distance that you're ruling out. But as long as delta and mu are constant, so you get a constant bound. Okay. So this is our main theorem. And in fact, in the spirit of Frankl and Rodl, you can think about a two-family version of this problem, where your first point is supposed to be in set U, and your second point is supposed to be in the set W. And for the two-family version, we get the same kind of bounds. So if you have two different sets, each of constant density, this probability can be bounded below by a constant. So the pairs that you have to check, you have to count are slightly different. For some technical reason, you have to count pairs at a distance d or d plus 1. But you get the same kind of theorem.
Do you also get something from u which is exponentially small, or
no. So I would like to pose this as an open question at the end. So you get something for u which is less than constant, but the bounds kind of break down when you get to u which is of density, say 1 over n or something like that. So in particular, it does not imply Frankl-Rodl. If you could get exponentially small, you would get Frankl-Rodl. Okay, so this is the main theorem. Let me tell you a little bit about the proof. Let me first tell you the high level, or the first step of the original Frankl-Rodl proof. So you want to show that if you have a set which is big, then there are pairs x and y that are at distance exactly d inside your set. So what you do is, first you reduce this problem to a related problem, where instead of counting pairs at distance d, you count pairs that share exactly d1s. Okay? So this problem reduces this to this other problem, and in fact this is closer to the original formulation of Erdos. But in this transition, you lose slightly in the density of the set. So if you start with a constant density set, you get a density of 1 over n or something like that. And then you prove the theorem here. The proof is complicated and combinatorial. Most of the work goes into proving this theorem. The reduction is kind of very simple. Now, the bad thing is that this first simple step fails for us. And the reason for that is that even if you start with a constant density set, you get a set which is of density 1 over n. So you can't really hope to show any bound on the probability better than 1 over n squared or something of that sort. So you can never show, even if you had very strong bounds for the probability here, you can't get a very strong bound for the probability there. You can never get to constant for the probability. So you need to do things differently. And what we do is that we reduce this theorem. So what we are interested in is bounding this probability by a constant. So we reduce it to a related problem. And here is the related problem. So in this setting, you choose a random x, and then you choose a random y, which is at distance exactly d. So what we reduce it to is this setting where you choose a random set x, and then you choose a random point y, where y is at expected distance d from the original point. So what does this mean is that at each coordinate of y, you either choose the same coordinate as x or differently, and this choice is done so that their expected distance is exactly d. Okay. So then this probability here, as it turns out, was studied before. So it was studied by Mossel, O'Donnell, Oded, and Sudakov and Steif. So they basically showed exactly the parallel of the theorem we are interested in this regime. So if you have a set of constant density, then if you choose x and y according to this distribution, where x is random and y agrees with x in each coordinate with constant probability, then the probability that x and y are in your set, it can be bounded by a constant. So it's at least a constant. And in fact, they proved a very nice explicit lower bound. It's probability. So what we do is we reduce our problem to this case. Now, to say a few words about this thing, so one nice thing about this probability distribution is that, for example, it's a product distribution. So x1, y1 are jointly distributed, but they're independent of x2 and y2. And that makes the analysis of this probability much nicer. And so the techniques used are Fourier analytic kind of techniques. So that makes the problem much nicer. Yeah, so in fact, a two-family version of this theorem is true, and our two-family version of our theorem reduces to this two-family version.
So in the second setting, can you be exponentially small?
Yes. So actually, in this setting, you get a very, very explicit bound here. So, if maybe I have the bound on the next slide. Well, okay. So you get a bound which is a certain power of mu. And which power it is depends on your delta. Okay, so it works for any mu. But the thing is that when we reduce this problem to this problem, we have a little of one factor which comes into the picture additively. And that would mean that if this bound gets small enough, which it's going to get when your mu is very small, that additive term is going to make the theorem kind of meaningless. So the constraint that mu has to be can't get exponentially small comes from the reduction, not from the theorem. Now, okay, I will talk about this a little bit more near the end. Okay, so let me tell you a little bit about how we do this reduction. So the way the reduction is done is that you have these two probabilities. One is under our distribution and one is under their distribution. And what we show is that these two probabilities are, with a little bit of cheating, are always very close. So we show that the difference of these two probabilities is little of 1. So if you get a lower bound here, you get a lower bound there. And even if you get an upper bound here, you also get an upper bound there. So they're very close. Now these two probability distributions are not close, say, in a statistical distance or anything like that. So, but we can show that the two probabilities are close, and the way we do it, well, the first few steps are pretty standard. So, so you want to show that the difference is little of 1. So you define this characteristic function of the set, which is 1 when x is in the set and 0 when it's otherwise, and then you can write your probability in terms of an expectation, where here x and y are taken under this weird distribution, and here they're taken under this nice distribution. And so as it turns out, the second expectation is a well-studied kind of object. So you can think about it as there is this standard important linear operator called the Bonomi-Beckner operator. So this is a linear operator acting on these functions. So t of a function f at a point x is just the expectation of f of y, where y is chosen kind of in a correlated way to the x. So exactly like how y is chosen here in a way where each coordinate agrees with x with a certain probability and different with a certain probability. So the same kind of distribution is a distribution you take this expectation over. So once you have this linear operator, you can write this expectation as expectation of x of 1 sub u of x times this operator applied to 1 sub u of x, 1 sub u at point x. So what you're interested in is how does this linear operator change your function. And in the same spirit, you can define another linear operator for the probability we are interested in. It's exactly the same, except that here you are doing an averaging on this in this nice way. Here you are taking the averaging over all points of the distance exactly d. So what we show is that these two operators are close in a precise sense. So they're close under L2 to L2 operator norm. Well, okay, so that's not precisely true, but something along those lines is going to end up being true. Okay, so So both these operators are linear operators, and as it turns out, the Eigen Vectors are the same. So both their Eigen Vectors are the Fourier characters. They're the parity functions. And so both of them have n+1 repeated eigenvalues, and I have kind of plotted them here. I don't know if you can see them. Well, let's see if I have. Okay, so here are the plots. So here is the case where, say, n is 25, and the blue thing is the eigenvalues of the T operator, the Bonomi-Beckner operator, and the green thing is what we are interested in. So what we show is that each of basically these two curves are always close. That each eigenvalue of this operator is close to the corresponding eigenvalue of the other operator. Now, so you have to break this in. So the set of all eigenvalues into a few different subsets and do it differently.
Does this just mean which eigenvalue you're in? The eigenvectors correspond to inner products with different vectors, and it's symmetric. So all that matters is the Hamming weight.
Yeah, exactly. That's precisely why you have n+1 repeated eigenvectors. So they correspond to different Hamming weights, and their corresponding eigenvalues are going to be close. Yeah. So it's pretty simple to see that which are the eigenvectors. So the question is, how do you show that the eigenvalues are close? So I mean, from this plot, it kind of looks like they're somewhat close in the first half for the first 15 or so eigenvalues. For the second half, you can see that they're not close at all. Okay, so
the left is the high eigenvalue.
yeah, the left is the high eigenvalues. I mean, so the eigenvalues start at 1. So the T operator's eigenvalues go to 0 exponentially fast. This other thing goes to 0 pretty fast, but then once you get to the middle, it starts growing again, and it has another 1 eigenvalue at the end. So this is for the case where n is 25 and the d is 6. Now, the way that we get rid of this is that that thing near the end is whether it goes to 1 or -1 depends on the parity of d. Okay? So if I go to d equals 7, they will be like this. So this would mean that you add up the SD with SD plus 1, and then you can show that they're close.
These green ones are the Krautchuk balloon?
Yes, precisely. So as it turns out, this green thing is up to some normalization equal to the value of the Krautchuk polynomials, and actually we use several properties of them to show that these two things are close. So both curves are pretty well-studied type of objects. Okay, so yeah, so there are these two curves, and you add them up to get the eigenvalues of SD plus SD plus 1, and that's a good approximation of the T operator. So you get that the two operators are close.
But do you know the answer? Just if you don't allow this cheating, what happens if you just really care about distance d?
Yeah. So
Even and odd sets.
yeah, exactly. So the set U is the even points, say. Then it doesn't have any odd thing. And so there is a question related to this. So in the two-family version, you really need d and d plus 1. But I mean, you really need two distances ruled out of different parity. So we can only show it for d and d plus 1. But you can ask, what happens if I have a set which doesn't have distance d and d prime where they have different parities? Can you show something there? So this kind of adding up completely breaks down there. But so this kind of concludes the first half of the talk. So you show this these two operators are the same in this sense, and that would mean that when you take when you apply them to this one U function, you get essentially the same functions, and the two expectations have to be pretty close. Now, how close these two eigenvalues, these two operators are, gives us what is the little of 1 in additive factor in the distance of the two expectations. So what we can show is that they're close up to, say, 1 over n to some power. So that's kind of reason in the calculation why we get a somewhat weak bound. Okay, so there are two open questions. One is to improve this error term, this little of 1 term, and if you could push it to exponentially small, you would get a completely new proof of the Frankl-Rodl theorem, which would be density version and also completely analytic. So it would be very different in nature from the original proof. I think this was a very interesting open problem, and.
Did you say how d and you get rid of the d and d plus 1 condition if you use the same set?
Okay, so that's another kind of small trick. So this machinery gives us the 2-family version where we are interested in this sets of distance points of distance d and d plus 1. Now, if I have just one family, I can get rid of this d and d plus 1 simply by saying, okay, look at your set, look at either all the even points or all the even parity points, all the even Hamming weights, or all the odd Hamming weights. So, whichever you look at, one of them has to have density at least half the original thing, and whichever you look at, it's not going to have any odd distance. So, when I count d and d plus 1, d plus 1 is not going to appear at all. Okay, so that's so improving the error term and getting a new proof of Frankl-Rodl is one open question. Another is that so in the original paper they show the density version. Frankl and Rodl show density versions of show other variants of the same kind of theorem. So one was the thing that we saw. It's where you look at the points and you count the number of points which share the ones. So there are some other variants. So you can imagine density versions of those, and you can ask if the density versions hold. Now, as it turns out, most of these theorems that Frankl and Rodl studied in their original paper reduce to each other pretty easily, but their density versions don't reduce to each other, because this reductions kind of in these reductions you lose a polynomial factor in the density of the set. So it seems that you need a direct proof.
Is there any reason to believe the density version, even for the original? Did people try to?
So yeah, okay. So actually, Frankl and Rodl showed some density version for the variant where you are counting the number of points which share a certain number of ones. So it's not a very strong one. So it holds for sets which are exponentially small, unlike our theorem, but it can never really give you anything like the probability is constant. So it's a kind of a different formulation, but they do prove lower bounds on the number of points. So some version of it is true with some parameters. It's true. I don't know if it's.
The density is more than.
Yeah.
So it talks about more than a linear number of pairs.
Yeah. So actually, the correct way to imagine it is they prove something like almost all pairs are at distance d in the set you have selected. Now this can't be, of course, true, but what they show is that so almost means 1 minus epsilon raised to some power of n. So so you can show so if you look at all the pairs at distance d which are inside f, you can lower bound it by the size of f squared times 1 minus epsilon to the n. So it's a strong bound, but it can't really give relative to the number of edges. Okay. So if there is no questions, I will move to the second part. Okay. So this is about applications of this theorem to integrality gaps in bounded degree graphs, and I will say what integrality gaps mean and what's the problems we are interested in. So this is going to be somewhat independent from the first half of the talk. So let's start with something you probably all know. So the vertex cover problem, you have a graph and you are interested in finding a subset of the vertices which touches every node. And the size of the subset is minimized. So the complement of the subset would be an independent set. The subset would be a vertex cover. So here is an example for 5 vertices. So it's a standard NP-hard question. It has been studied extensively. So the best algorithm known for vertex cover is 2 minus the 2 of 1 approximation. So you can always output a vertex cover which is at most a factor 2 bigger. And for independent set, it's an n over poly log n factor. So getting a 2 approximation for vertex cover and n approximation for independent set is trivial. So all you save is this little of 1 and that polylogarithmic factor. And there have been quite a few papers on getting better and better bounds on this. So the current best are Dukarkostas and Feige. And then you can show that it's NP-hard to get better than 1.36 for vertex cover and n to the 1 minus epsilon for any epsilon for independent set. And if you believe the unique games conjecture, then that 1.36 will become 2 minus epsilon for any epsilon. Now, the best algorithms for both of the problems come from semi-definite programming. And then you can ask yourself, so what is the limit of semi-definite programming? So what's the limit of the standard semi-definite program that has been used? Or what if I try and come up with a very clever linear or semi-definite program? Can I break this 2 minus little of 1 or n over polylog n barrier? And this has been studied extensively, and the answer is essentially no. So I won't go into the details. So there are multiple incomparable results, but the answer is mostly no. You can't break it by much. Now the problem we are going to study is vertex cover and independent set when the graph is bounded degree, say the degree d. So you should think of d as a very, very big constant. Okay? So here, so the best algorithm is something of the form 2 minus 2 times log d over log d. So you save an order log d over log d over the 2 approximation. And for independent set, the best algorithm is d log d over log d. Again, a d approximation is kind of
This d should be n.
No. It's
the
the
independent set should be about n over d, right? In a degree d graph, you're trying to maximize the independence.
So no, this is the approximation factor.
Oh, the approximation.
Yeah. So a greedy algorithm would get a independent set of size d. Which is n over d. Yeah. Okay. So these. So in independent set, you save a factor log d over just the trivial greedy algorithm. Again, these two algorithms are semi-definite programming type of algorithms. And there is some NP hardness known. It's not very strong. It's d over some factor which is sub-polynomial for independent set. And if you assume the unique games conjecture, well, we know that this algorithm is essentially tight. That you can't really break this 2 minus log d over log d barrier. There is some lower order terms that you might be able to improve. For independent set, it's not tight. So the best algorithm is essentially d over log d. The best hardness that's known, even assuming unique games conjecture, is d over log squared d. So a natural question to ask is, which one is optimal? Should we start trying to improve the algorithm or the hardness? Okay. So in order to study this, you can ask what is the limits of the linear programs or semi-definite programs for this problem. What if we look at crazier and crazier linear or semi-definite programs for both problems? And this, a way to formalize this is to study this concept of integrality gaps of the relaxations. So I will define it in a little bit, but think about it as kind of a lower bound for how good algorithms based on these are. And so here we prove two lower bounds for vertex cover, we get a 2 minus order log d over log d for some strong families of semi-definite programs. And for independent set, we get a lower bound of d over log d for a strong family of linear programs. So these come from these so-called hierarchies, and the first one is in the Lovász-Schreiber semi-definite hierarchy. The second was in the Shirali-Adams LPR hierarchy. So I will get into these later. But if you believe that the lower bounds on these linear and semi-definite programs hint at the correct approximability of the problem, this indicates that the algorithms should be essentially tight, and the unique game's hardness is what you should be able to improve. And in fact, I think this is a very interesting problem. Can you improve the unique game's hardness for independent set from d over log squared d to d over log? So our results are these lower bounds on these integrality gaps. So let me tell you what are these integrality gaps. Where do they come from? Okay, so let's say we want to write a linear program for vertex cover. For the rest of the talk, I will talk about vertex cover, but everything applies to independent set. So here is a way to write an integer program. So you have these variables, xi's, which take 0 and 1 values, and they're supposed to, the xi is 0 if the vertex I is not selected as part of vertex cover, is 1 if it is selected. And the only constraint that you have is that if you have an edge between vertex I and j, the variable xi plus the variable xj has to be at least 1. And then you want to minimize the sum of xi's. Okay? So this is an integer program which perfectly formulate vertex cover. The optimum values here corresponds precisely to the minimum vertex cover. And then you can't really optimize over such things. You can't really find the optimum. So you relax it, so to speak, to a linear program where xi's can take any value between 0 and 1. And now the good news is that we can optimize and find the optimum of the right-hand side thing precisely. The bad news is that it might not have anything to do with an actual vertex cover. So the integrality gap is defined as the ratio between these two. So if so the right-hand side minimum is always smaller than the left-hand side because you're allowing for more values for xi's. So if integrality gap is close to 1, it means that in this relaxing you haven't lost much, and you can get a good approximation for vertex cover. And so it's the standard for how good these relaxations are. So it's easy here to see that the integrality gap for vertex cover is at most 2. You can just, if you have a solution for the right-hand side program, you can just round each xi to the nearest integer, breaking ties in favor of 1, and you get a solution for the left-hand side. None of the xi's is going to increase by a multiplicative factor more than 2. So the optimum on the left-hand side is at most twice the optimum on the right-hand side. So sadly, it's not very hard to see that the integrality gap can be actually as bad as 2 here. In fact, for the right-hand side, xi equals half is always a solution, no matter what your graph is. So your objective function is never more than n half. So what you can do, and what these hierarchies come from, is you can start with this relaxation, which you know is not a very good relaxation. And you can think, okay, how can I make it a stronger relaxation? How can I add more constraints to it to make it better? And so the way I think you should think about this is that you would want xi to be the probability that the vertex I is selected. It's a 0, 1 value. It corresponds to the vertex I. So you would want to think that there is a distribution mu over vertex covers. So this is we have in mind, and xi is really the probability that I is selected according to this distribution. Now, if this was the case, the solution you had would correspond really, to a vertex cover. There would be no integrality gap. Everything would be perfect. This is not the case, but it's good to think about it this way. Now, one thing you could do to make this linear program stronger is to say, okay, if xi's really come from such a distribution, we can add more information from the distribution into our program. So we can add more variables and more constraints to encode more information about this distribution mu. And here is, say, one set of variables I could add. I could add a variable xij, which is supposed to be the probability that I and j are in the set at the same time. So this corresponds to like the marginals on two variables. It's not really, you can't really deduce this value from xi's. So I can add this as a variable. And if I have these variables, it's easy to check that for all I and j, xi plus xj minus xij has to be positive. And the reason for this is that if xi is the probability that I is in the set, xj is the probability that j is in the set, and xij is the probability that they're both in the set, that value there is just by inclusion exclusion the probability that at least one of them is in the set. So it's a probability, it has to be positive. So I can add this as a constraint. So this will make the LP stronger because in principle there could be values for xi's where these xij's could never be defined in this way. So xi's that don't correspond to a distribution might be ruled out by this type of constraint. And in fact, you can say, okay, why would I stop at sets of two variables? I could add xijk's, which correspond to probability that I and j and k are in the set, and so on and so forth. And if you do this, continue to bigger and bigger set, you get an equivalent formulation to the Shawley-Adams hierarchy. So you get something that is actually pretty strong if you go far enough. So this is one thing you can add. Here is another thing you could add. You could say that if these xij's, now that we have added them as variables, correspond to the moments of the probability distribution. So you can make a matrix where coordinate ij is just xij, and this matrix is going to be a positive semi-definite matrix. It's not going to have a negative eigenvalue if xij's really come from a distribution mu. So you can add this as a constraint to your program. Now this constraint is not a linear constraint, but we can still optimize over it in polynomial time. So in fact, if you add just this, you get something which is essentially equivalent to the semi-definite program for vertex cover. So just adding this positive semi-definiteness really makes the formulation stronger. So you can imagine, sitting down and deriving other valid constraints that you could add to this, or alternatively, you can look at these hierarchies, which are kind of an axiomatic way of generating this kind of inequalities that are valid for true solutions that really come from a distribution.
I'm missing something. So why couldn't all the xij's just be 0?
Okay, so I cheated a little bit. Actually, adding xij's for vertex cover doesn't help. Yeah, so you can set all of them to be 0. But if I added xijk's, then you couldn't just do that. So you would have more complicated inclusion exclusions. Yeah, so 2 levels is actually not very good. In fact, I mean, any value you assign to xij's between 0 and 1, at least on the edges, you would be all right, because this is already weaker then. Yeah, but you can go, you can add more variables, and so what are these lift and project methods or hierarchies? So there are axiomatic ways to add these relaxations, deriving new valid relaxation and adding them to the program. So they usually have a parameter which we call level or L, which adjusts the strength. So if you start at L equals, so you start with the program for your problem. It could be any problem. So let's say vertex cover, and you apply this lift and projects methods up to level L. Now, if L is 0, you haven't done anything. You have the original program. If L is, say, 3 or 5 or another constant, you will get a program which you can optimize over in polynomial time. So optimizing it will still be in polynomial time. But if you go to much higher L, say L, which is n the number of variables, you get exactly the set of integral points. So you get to really to perfect vertex cover. You have a perfect formulation of vertex cover. So in between, you get a nice trade-off between how fast you can optimize over your program and how strong it is. So these are, the linear program or semi-definite program used in many algorithms, optimization algorithms, is actually weaker than applying these to a standard program for, say, L equals 4 or 5 or something like that. Looking at increasing L has been used in programs, in optimization algorithms. So the list is much bigger than just these 3 results, but so it has been used in, say, coloring, minimax allocation, and recently by Barak et al., they used it to devise sub-exponential time algorithms for unique label cover. So they looked at L, which is not quite n, it's say n to the epsilon, and they showed that if you go to such a high level, you can get a program which really outperforms all polynomial time algorithms we know about. Well, this was kind of a reproof of an earlier work of Aurora et al., but in this kind of language. And on the other hand, people have studied trying to say that even if you go to high levels of these programs, you can't really beat the algorithms we know for various problems. So both positive and negative sides have been extensively studied. So here is a kind of a again, not exhaustive list. There are much more results than this. In the last one, for example, Regev and Sturer showed that even if you go to more than a constant number of rounds for another of these programs, you can't beat the best known algorithms for unique label cover. So for the problem of unique games, we know both negative and positive sides for different hierarchies, for different lift and project methods. But it's pretty well studied.
Can't you use this integrality gap for unique games and the reduction from unique games to
no, you can't. So as it turns out, you can. So maybe that's also appropriate to say here. There is a very formal relation between lower bounds in these hierarchies and unique games based hardness of approximations for many problems. So you can either, if you have a unique games hardness, you can find a lower bound for these hierarchies, in these hierarchies, and if you have a lower bound in these hierarchies, you can show a unique games hardness. So this does not apply to vertex cover. It applies to constraint satisfaction problems, a very big family of problems, but it does not apply to vertex cover. So we can talk about this after the talk, why it doesn't. But okay, so what we do is we prove lower bounds in 2 of these hierarchies for vertex cover and independent set in bounded degree graphs. Okay, so you want to prove a lower bound in any hierarchy or hardness of approximation in degree bounded graph. So natural way to do this is to start with a lower bound for general graphs and then try to do some form of sampling to make your graph bounded degree. So that's the way the hardness of approximation was done, and that's how our result is done. So you start with an integrality gap for vertex cover in bounded degree graphs. So this means that you have a graph where the relaxation, where the graph does not have small vertex cover. If a set S is small, then there is an edge outside of the set that this set misses. So any small set is not a vertex cover. On the other hand, the relaxation thinks that it does have a small vertex cover. The value of the relaxation is small. Now, what you do is that you do simple sampling of this graph. You sample enough edges such that the average degree becomes, say, d over 2. Okay? So once the average degree becomes d over 2, you let this be G tilde. It's also pretty easy to see that with a little bit of modification, you can make the maximum degree d. Okay? So you had this original graph. You did some sampling, and now you have a bounded degree graph. So what you really want to show is that this is still an integrality gap instance. So still the value of the relaxation is low, but the graph does not have a small vertex cover. So as it turns out, usually the hard side is proving that the value of the relaxation is low. But here you get that for free, because you had an original graph, you deleted a bunch of its edges, so the value of the relaxation will go even lower. So if in the original graph the value of the relaxation was low, now you have deleted a bunch of edges, you have less constraints, so the value will go even lower. The question is, how do you show that the graph does not have small independent sets, or alternatively big small vertex covers, or alternatively big independent sets? So if you have a small set S, how do you show that there is an edge outside of it? Now, this actually is equivalent to a density version of this statement. So if for any small set S in the original graph, you know that there were many edges outside of it. When you do the sampling, chances are you will hit some of these edges. So this edge will appear in the edge set of this thing. So what you have to show is exactly that the complement of such a small set is always dense. So any big set is dense. Now, that's how our result from the first half comes into the picture. As it turns out, at least in quite a few of these results, the graph used is this Frankl-Rodl graph. So it has vertices which are 0, 1 to the n, and vertices are connected if their Hamming distance is exactly some constant times n. So, in the previous results, they had to use the Frankl-Rodl theorem to say that the graph does not have any small vertex covers. So what we need is exactly a density version of the Frankl-Rodl theorem. You have to show that the so you have to show that any small set, the complement of any small set has many edges inside of it. So it's exactly a density version.
So I guess you cannot, for the integrality gap, use another version of the theorem.
Well, that's a very interesting question. So if I changed my graph so that the edges are, instead of at distance some constant times n, at distance that constant plus minus, say, square root n, okay? Then I could just use the Odets theorem. So as it turns out, for some hierarchies that's an integrality gap instance, for others it's not. Anything that has this positive semi-definiteness constraint, it seems that adding edges at all these distances makes your life much, much harder. So I don't think there is a proof that that's not an integrality gap instance for any hierarchy, but it definitely makes the constructions break in a very serious way. So you can get some integrality gaps, but not all of them. Okay, so to make it explicit, we show that any constant number of the Lovász-Schreiber STP hierarchy for vertex cover in graphs of maximum degree d has integrality gap 2 minus order log d over log d, and this is by applying this kind of construction to a result of Georgiou et al. And we also show that any constant number of the Charlie-Adams LP relaxation for independent set for graphs of maximum degree d has integrality gap d over log d. And this is applying this kind of construction to another result of me with Georgiou. So a few open questions is one, which I think the most interesting is can you show unique games hardness, better unique games hardness for independent set in degree bounded graphs? So our work seems to suggest that you should be able to. And the other thing is you can, so we have results in 2 or 3 different hierarchies. You can think of extending them to other hierarchies. And it seems that it works in some hierarchies but breaks in a serious way in others. So that's it. Thanks.
If you go, so let's say we go inside that worse than what you can get from 3 levels of the hierarchy?
That's a good question. I don't know the answer. I'm trying to think. I think that the best known algorithm actually comes from something like 2 levels of the hierarchy. It's a pretty small constant. The other thing is that you have improvements all the way to n. Now, but the real question is does it stay the same and suddenly jumps at some point, or, yeah. So I don't know.
You don't really care about the exponential small for your application.
Yeah,
you
yeah.
don't really care. You got
Yeah,
what you
yeah.
wanted from the-
Yeah. So it seems that in CS applications you never care. Actually, what you do care, not in our application but in previous applications, is what happens if this distance that you're ruling out, this distance that doesn't exist, is not order n. So it's something like n minus little o of 1. But then you don't care about the density so much as long as you can show that it's less than a constant. Or,
So you don't really need Frankl-Rodl. You just
yeah.
need to talk about sublinear size.
Yeah. Sublinear. Yeah. But so sublinear size when the distance is very close to 1. Yeah.
So your result you said is kind of analog of the noise sensitivity version,
Mm-hmm.
and that's the reverse kind of theorem for the small set expansion of the hypercube. So you're
Okay.
saying that if you have large sets, then like many edges land within the set.
Yes.
So is that converse to your statement that?
Well, it would be Frankl-Rodl.
I mean, if you take a set which is very small, then there'd be many edges.
Going outside the set.
So that is true for the noise sensitivity graph.
Let me think a little bit. Well, I think I don't know. I think in principle you should be able to show it, but you run into the same kind of problem with this little of 1 factor. See, because okay. So to put it another way, not only do we show that a lower bound implies in the noise model implies a lower bound in this kind of Frankl-Rodl model, it also, the way it's done, it means that an upper bound would also imply. So you can look at the 2-family version where the one family is the set, the one set is the original set and the other set is the complement, and so the statement can be written in such a way. The problem is, because your set is very small, the lower bound that you get is meaningless because of that little of 1 factor. So if you could improve the little of 1 factor, I would guess that it would answer your question. But as is, probably not.
Okay, thanks, guys.
Thanks.